All right, everybody. In this video lecture, we are going to talk about volume. So the past couple classes, we've talked about two other factors that affect how gases behave. We've talked about pressure and temperature. And so now we're just moving forward. Today we're going to talk about volume. Volume is a topic that maybe you're already somewhat familiar with from your math classes, right? Volume is length times width times height. But in chemistry, we are going to define volume as the amount of space occupied by a material. In particular, the amount of space occupied by a gas, right? Because we're talking about gases. So the volume is the amount of space occupied by a gas. And there are two types of containers that we talk about when we talk about volume. We've got rigid containers. Rigid containers have a constant volume. So I know that the note sheet is a little messed up on this, but so just cross out the blank. But you should know rigid containers have constant volume, and flexible containers have a variable volume. Now, if I was trying to come up with examples of these types of containers, this is what I might say. Any flexible container is going to have a volume that can change, so that can increase or decrease. The first thing that comes to my mind is a balloon, because you can blow up a balloon, you can make it bigger, you can make it smaller. It has a variable volume. Some other examples of flexible containers are basketballs, soccer balls, volleyballs, etc., car tires, things of that nature. Anything that can sort of stretch its boundaries. Even plastic water bottles can be flexible, like the Dasani or Aquafina type water bottles. But maybe you're looking at your water bottle and you're like, man, this is pretty hard plastic. Or maybe you have a metal water bottle. Those are types of containers I would consider to be rigid, right? A rigid container isn't going to be able to change its volume. It's going to have a constant volume the whole time. And when we think about these containers, we need to, as we move forward, when we talk about examples, we need to keep in mind, do we have a rigid container or do we have a flexible container? Because if we have a rigid container, then the volume can't change. The volume has to be the same the whole time. And so today when we talk about Charles's law, we have to have flexible containers. All right, so there are some common units of volume that we sort of discuss in chemistry. One that you're probably pretty familiar with is that 1 liter equals 1,000 milliliters. All right, those are metric units that you learned probably earlier in the year. A unit that you are probably unfamiliar with in chemistry is centimeters cubed. But remember when I said volume is length times width times height? Well, that's centimeters times centimeters times centimeters. So that's how you get centimeters cubed. And actually, 1 centimeter cubed is the definition of a milliliter. That's how they defined the milliliter when they started using the liter metric system for volume. The last bullet point that I have up here is so that we can go from something small, something with centimeters cubed, to something bigger, meters cubed. And so that's the conversion between centimeters cubed and meters cubed. And now that I've shown you these conversion factors, it's probably time for us to do some conversions ourselves. So let's convert 182 milliliters to liters. Just like the conversions that I did with pressure, the first thing that I'm going to do is, all right, 182 milliliters. And I'm going to put that immediately over 1. Remember that the 1 is just a placeholder. Then I'm going to set up my fraction. The unit that I'm canceling out of goes on the bottom, so milliliters goes on the bottom, and liters goes on the top. And then I fill in this information with the numbers from before. All right, so I can see that there is 1 liter, and that's equal to 1,000 milliliters. So I put a 1 by the liters and 1,000 by the milliliters. So now I'm ready to sort of cancel out my units. Milliliters cancels out with milliliters. And what I'm left with is 0.18 2 liters. All right, let's do the next one. Let's convert 803 centimeters cubed to milliliters. So let's start with 803 centimeters cubed, and that's going over 1. Remember, the 1 is just a placeholder. I multiply that by another fraction. Centimeters cubed goes on the bottom because I'm trying to cancel out of that unit. Milliliters goes on top, and then I fill in the numbers. And in this case, it's actually 1 and 1. Remember that 1 centimeter cubed is the same thing as a milliliter. So those will cancel out with each other. Centimeters cancels out, centimeters cancels out, and what I'm left with is the same thing that I started with, 803, but this time I'm in milliliters instead of centimeters cubed. All right, last one. Let's convert 2 meters cubed to centimeters cubed. So 2 meters cubed over 1, and now I've got 1 centimeter cubed on the top, and then 0.0000001 meters cubed on the bottom. Now when you go to type that into your calculator, be very careful that you have the right number of zeros. But what you'll end up getting is 2 million centimeters cubed. The meters cubed both cancel out with each other. All right. So if you're feeling pretty okay with these conversions, you can go ahead to the next part of the video. Otherwise, feel free to pause the video and review the material that we just covered. So now we're going to move on to Charles's law. In Charles's law, we are examining the relationship between temperature and volume. And so this law is also known as the temperature-volume law. And this law states that temperature is directly proportional to volume when pressure is held constant. So let's think back. What does it mean to be directly proportional? If two things are directly proportional, then if one changes, the other one is going to change the same way. So in our case, if the temperature increases, then the volume will increase. And if the temperature decreases, then the volume will decrease. But let's think about that, because I just talked about changing volume. So what kind of container do I have to have? Rigid or flexible? If I'm changing my volume, I have to have a flexible container. And this bullet point is not on your notes anywhere, so make sure that you write that down to the side of your paper. So we have to have a flexible container. And then, like I said before, temperature increases, volume increases. Temperature decreases, volume decreases. But why is that? So go ahead and brainstorm for a second. Why does the volume increase when the temperature increases? In fact, what happens is that when temperature increases, gas particles move faster. Hold on, let me move this so that you can actually see what it says. When temperature increases, gas particles move faster and exert pressure on the walls of the container. But we have a flexible container, so the walls of that container can actually move outwards to account for that pressure being exerted. And that increases the volume, but it keeps the pressure constant. So gas particles are moving faster and faster, meaning they're colliding more with the walls of their container, and those collisions just push the walls out. So that's how you can sort of describe what happens when temperature increases and therefore volume increases. But can anybody think of what happens when temperature decreases? Why does volume decrease? Anybody think of that? Well, obviously this is a video, so I can't interact with you directly, but hopefully you thought of something. I'll let you know, though, that when temperature decreases, the particles are moving slower. And so the particles are moving slower, meaning that they are not colliding with the walls of the container as much, which means that normally pressure would go down. But pressure has to be kept constant, so the volume of the container decreases to account for that change in pressure. Very similarly to what you saw in the lab today when the can was crushed. All right. So those are the main bullet points having to do with Charles's Law. Now let's do an example problem together. So example 1 states that at 273 Kelvin, the helium gas in a balloon, they said balloon, so we have a flexible container, has a volume of 20.0 centimeters cubed. If pressure remains constant when the temperature increases to 291 Kelvin, what is the volume of the balloon? So this problem is going to work out very similarly to the Gay-Lussac problems that we did for homework last night. And so the formula that we are using, instead of P1 over V1, P1 over T1, it's V1 over T1 equals V2 over T2. Now the first step, remember, to solving these word problems is pulling out the given information. So I am going to go ahead and underline this given information. It says 273 Kelvin, and that's going to be our T1. T1. Do we have to worry about converting it? No, because it's already in Kelvin. All right, then it says the helium gas in the balloon has a volume of 20.0 centimeters cubed. So that's volume 1. And then it says pressure remains constant, so we don't have to worry about pressure. But then the temperature increases to 291 Kelvin. So that's going to be our T2. And then the question asks, what is the volume of the balloon? So it looks like we need to solve for V2. That's a big question mark right now. So let's go ahead and plug that into the equation. V1 is 20.0 centimeters cubed over T1, 273 Kelvin. And we set that equal to volume 2, but remember, we don't know volume 2, so we just write V2 over T2, 291 Kelvin. All right, if you've been following along, then hopefully you can predict what the next step is. We need to cross multiply. All right, so now what we get is 20.0 centimeters cubed times 291 Kelvin, and that equals 273 Kelvin times V2. Remember, we are trying to solve for V2, so how can we get V2 by itself? How can we get V2 by itself? Well, we are going to have to divide both sides of the equation by 273. So divide both sides by 273 Kelvin. All right, and now let's see what cancels out. On the right side, both of the 273 Kelvins cancel out. On the left side, both of the Kelvins cancel out. So the only unit we're left with is centimeters cubed. And if you go ahead and do this math, you do 20 centimeters cubed times 291 equals divided by 273. And you should get that volume 2 equals 21.0 0.3. And the unit is centimeters cubed. Centimeters cubed. All right. So that's how you do these Charles Law examples. Thank you for bearing with me as I wrote all of this using the mouse on my computer. For the rest of class, what you should work on is example 2. I left the answer key with Mr. O'Donnell, so go ahead and everybody needs to work on example 2, and then he can check your work when you're done. And then the rest of class you can spend working on your homework. It's just a reading, and you just have to answer one question. So thank you for watching this lecture. I will see you guys on Monday. Don't forget about your quiz on Monday.